Welcome to today's Explainer. If you're in engineering or system design, you already know the inherent challenge of the field, right? How do we take these highly visual, intuitive engineering graphs and actually translate them into the rigorous, universally understood math that we absolutely need for deep analysis? Well, that translation process is exactly what we're tackling today. We're going to explore a really systematic method that basically bridges the gap between the drawn topologies of physical systems and the concrete algorithms that computers use to simulate them.
So how do we turn a visual diagram into a rigorous mathematical equation? Okay, let's dive into this. In system design, drawing out a physical system is really only the first half of the battle. A picture is great for human intuition. It helps us, see the components and how they physically connect to each other. But human intuition just isn't enough when you need to simulate complex edge cases, optimize control systems, or mathematically guarantee stability before a prototype is even built. For those heavy lifting tasks, we need hard math. We have to have a way to seamlessly cross over from a drawing on a page to a mathematical model that computational software can actually process.
Section 1. The Visual Math Divide. We're starting out on the shores of visual diagrams before we cross over into mathematical analysis. To make this crossing from visual to mathematical, we first need to understand the tool we're starting with, the causal bond graph. Now, the absolutely crucial point here is that a causal bond graph isn't just some simple sketch of springs, masses, and dampers. No way. It actually functions as a deeply compact set of first-order differential equations, just waiting to be unlocked. The bonds in these graphs represent the physical power flowing through the system, specifically the effort and flow variables. And those little causal strokes you see at the ends of the bonds, they're literally dictating the direction of cause and effect throughout the entire system network. Because power flow and causality are explicitly defined in the drawing, the underlying differential equations are inherently built right into the lines and arrows. It's like a giant puzzle with the math already baked in.
Section 2 meets the master formula. This is where we introduce the ultimate translator to help us cross this divide. Since the causal bond graph effectively stores all these differential equations, we obviously need a reliable way to extract them. Enter the master formula. Think of this as a kind of mathematical superpower. It's a highly systematic approach used to transform causal bond graphs directly into complete state-space mathematical models. The true technical brilliance of this formula is that it handles all the complex sorting of independent and dependent energy storage elements for us. Instead of relying on messy, error-prone algebraic substitutions by hand, which, let's be honest, nobody wants to do, the formula automatically evaluates the causality to output the clean matrix form. It completely removes the guesswork and gives engineers a repeatable engine for high-level mathematical extraction. It's a real game changer.
Let's move to and see how this builds, stepping through this overarching process together. Step 1, we start with the visual causal bond graph, which logically maps out our entire physical system. Step 2, we apply the master formula. In this absolutely critical step, the formula parses the graph node by node, evaluating those specific causal strokes we talked about to systematically map out the system dynamics. And finally, step 3, by processing these relationships, we systematically derive the complete mathematical model. It's just a direct, incredibly robust pipeline from visual engineering topology straight to pure analytical mathematics.
Section 3. Inside the interactive lab. Let's mentally step into a laboratory where we can actually see this process happening in real time.
Picture an interactive lab environment designed to teach this very concept. You've got a split-screen setup. On the left side, you map out your physical system using a visual causal bond graph, where every component and energy exchange is accurately represented. Now imagine that every time you click on a specific bond over on the left, its corresponding mathematical equation instantly pops up on the right. Bam, just like that. You're no longer just looking at abstract geometry. You're experiencing how the visual topology links directly and immediately to the math. Each interaction extracts a distinct, necessary piece of the mathematical puzzle based purely on how you designed the system's energetic connections. So, what exactly are we extracting from these interactions? Well, evaluating a bond reveals specific first-order differential equations governing energy storage in the system. For example, click one type of bond and you reveal its momentum formula. Here, the rate of change of momentum, P dot, equals the effort variable, E. Click another bond and you see the displacement formula. In this case, the rate of change of displacement, Q dot, equals the flow variable, F. Momentum and displacement, P dot equals E, Q dot equals F. The process just rapidly and systematically translates those energetic bonds into the foundational equations of system dynamics.
Section 4, the final state-space matrix. All of these individual pieces are about to come together into one finalized structure.
Now, what's really interesting about this slide is how all of those individual equations, all those p dots and q dots, build toward one incredibly powerful and elegant destination, the beautifully compact state-space matrix, x dot equals ax plus bu. By applying the master formula, we've gathered up all the independent dynamic relationships and structured them right into this matrix equation. In this format, the A matrix holds the internal system dynamics, the core physical characteristics and relationships. The B matrix precisely maps how the external inputs, our U, affect the system. And the state factor, X, well, that's built directly from those individual momentum and displacement variables we just uncovered. The geometry of the original drawing is now perfectly encoded into linear algebra.
Section 5, bridging engineering and analysis. Let's remember our overarching learning goal here, bridging that critical gap. This entire process provides a clear bridge between visual engineering diagrams and rigorous mathematical analysis. And this brilliantly illustrates why translating these systems is so essential in the real world. Once you've crossed over into the realm of rigorous mathematics, entirely new analytical worlds open up for us. Engineers can now run eigenvalue analysis to determine exact system stability. They can accurately simulate time responses to dynamic inputs, or even design complex feedback controllers. These are powerful analytical feats that you simply cannot accomplish by just staring at a drawing.
So now that we possess the master formula to reach the state-space matrix, x dot equals ax plus bu, what unseen behaviors of our physical systems can we finally predict, optimize, and control? You now have the mathematical model. The math is literally in your hands, ready to be applied to any physical system you can possibly map out. Think about that for a second. Keep exploring, stay focused, and I'll see you in the next explainer.